Thank you very much. Thank you all very much for the invitation, and I'm really glad to be here. I think this is the first time I give a talk, I think. Anyway, I'm going to talk about some, it's quite fundamental and general problem. That is, when you have climate forcing happen, force the climate system, how does the atmosphere, ocean, heat transport respond? Are they in compensation? It means the opposite direction, or in collaboration? That means they go the same direction. Okay, so that's the question. This can be called a kind of a generalized Bjerknes compensation problem, which most people have been thinking about, called Bjerknes compensation when they go opposite direction. Let's just start with this. Actually, this from original Bjerknes paper, it shows the total heat transport, atmosphere, and ocean. The detail, it doesn't matter right now, but the point is that, the question is that this is the mean climate, right? Atmosphere, ocean, transport heat toward the polar region. The question is, now if you have climate forcing, CO2, whatever, other things, do they increase simultaneously or decrease simultaneously, or do they one increase, one decrease? Okay, so that's a fundamental question. And it's actually, there's no theory on this, and there's no general. I was puzzled about a few years ago thinking about this problem. I don't have a rule of thumb for myself, So that's why I got interested in trying to figure it out. Go back to original Bjerknes hypothesis. Bjerknes had a paper a long time ago. It was a climate of 19th century versus climate of 20th century, early part, where he noticed that in the early part, the atmosphere, he can construct it from instrument data. It's called low index. That is, it's not very straight. It's kind of a very meandered meridional direction greatly. And and oppositely, in the 20th century, it's very straight, very strong jet. So then, here's his hypothesis. He thinks, in this case, it was because atmosphere transport more heat, because it go meridionally more easily. Atmosphere transport more heat. But the ocean transport less heat because you have weaker wind. So the Gulf Stream is weaker. So therefore, you cause this warm and cold pattern like this. Okay. Later, it was opposite. Wind is stronger this way, so you have less atmosphere heat transport, but stronger wind, increase Gulf Stream, increase heat transport. You warmed it up on the northern side. So he calls this, in this case, you can see that atmosphere and ocean, they go opposite. Now, so he put it here. He speculated the atmosphere maybe increase heat transport, ocean and reduce heat transport, and vice versa between these two scenarios. Okay. Now, it should be emphasized that it is a hypothesis because you look at his caption said that anomalies of heat flux in the ocean and atmosphere are assumed to cancel, leaving, if total heat flux and radiation on the top of the atmosphere remains unchanged. Okay, so he doesn't know what happened. He thinks like this. Now, think about this. If you have, let's suppose you have no heat exchange between top of atmosphere with the rest of the world. Whatever happened here, of course you have to compensate, right? That's very obvious. If you have no heat flux left here, if your ocean goes this way, atmosphere has to go this way. Okay, but now our real world, it's not like this. Because we have radiation from top of atmosphere radiates out, short wave come in. So our top is a leaky top, okay? It's not an energy flux zero. So therefore, it's actually not obvious when you have the ocean go this way, does the atmosphere go this way? It's actually not very obvious, okay? So this we call the Bjerknes compensation, and the atmosphere ocean heat transport response, that's delta. And if they go opposite direction, it means it's a compensation. The question is, how does that happen? Now, in climate models, we often observe that they are so robust, the sink compensation. They just give you all the examples from different model, GFD model, NCAR model, German model, whatever model. So one is this latitude, one is atmosphere heat transport, one is ocean heat transport. You see all of them? This is like in response to melting water in Greenland, AMOG collapse. You see all of them, then the ocean heat transport reduced, atmosphere heat transport increased. They're always opposite direction, okay? So in model, they found that it is very robust. There's another type of model. I think Tony did this kind of model, a lot of this kind of model for this problem is that you use a slab ocean. That means I prescribe ocean heat transport convergence through surface heat flux to the atmosphere. Then watch what is the atmosphere heat transport respond, okay? In this model, just give you an example, right? If I prescribe heat this way, and come out, convergence out, the atmosphere goes the opposite way. Okay, this compensation. All of the examples showing different parameter regime, they all show compensation. Okay, opposite. Now it's even more interesting to look at this. This larger than 1 means I have ocean heat transport this way, I have atmosphere heat transport even more than you have ocean heat transport. Okay, so that's kind of not obvious, right? How can I have more? Okay. So the point is that in models show lots of compensation examples. And it's also related to a very interesting question people have been getting interested in. I think Tony probably one of the first thought about this, is that, okay, if you have ocean heat transport, let's say Somos heat line changes transport. Let's say Somos heat line, you increase this way. Then assume atmosphere goes the opposite direction, then the entire Hazard circulation has to shift. Okay, so therefore it's related to, for example, why the ITCZ, the intertropical convergence zone, is to the north of the atmosphere, to the north of the equator nowadays. One argument is because Atlantic transport too much heat in this direction. The atmosphere has to go this direction. To do that, you have to shift ITCZ to the north of the equator, so the atmosphere energy is transported out the upper branch to the south hemisphere, compensate. Okay, that's under the assumption they compensate. Okay. Now, we also have examples where they don't have to compensate. Very simple example, in this case, in natural climate, when I have solar insolation come in, they both go the same direction. That's obvious. You know, you have extra heat in the south, in the equatorial region, have to transport that. At least that just says that, you know, when you have a general climate forcing, it's not always have to go the opposite direction, right? Even in this case, I said there might be compensation, but there's a very robust mechanism saying that they may not compensate. There may be collaboration. That is this, coupled hazard circulation and subtropical cell. When the hazard circulation is strong, the trade wind strong, you blow the Ekman wind stronger, then you blow the stronger subtropical cell. So now the hazard circulation transport heat to the north and poleward. The ocean also transport heat poleward. So this actually is a collaboration mechanism, okay? Very robust physical mechanism, okay? So the point is that they don't have to always compensate. And this recently, there are more experiments, numeric experiments. They were trying to test when we have high latitude climate forcing, how does that affect tropical ITCZ? You expect they have a compensation, ITCZ move a lot, but what you find in this fully coupled model is that there's very little response, okay? Very different from mixed layer model we talk about. See, this example, when you change the clouds in the south hemisphere, look at the ocean atmosphere heat transport, they are in the same direction and become very little when you go to equator. They are not opposite. This is another experiment you did with NCAR model in Arctic. You change the sea ice. Then you see the ocean atmosphere heat transport. Again, they are in the same direction. And there's very little atmosphere heat transport on the equator. Therefore, there's very little change over the ITCs. Okay? So the question that raises that, first of all, why in certain type experiments we have seen there, Bjerknes compensation is so robust? I showed you the first 2 pages, lots of examples. And, but in the meantime, why? It seems like there are also other cases where the atmosphere, ocean, they may not go opposite. So what is the condition when you will have them compensation, when you have them collaboration, right? The general problem, climate dynamics problem, okay? And in the first part of the problem, I call it the narrow sense Bjerknes compensation theory. You want to know why it's robust. Also, you want to know any theory, if you have to know why under some condition the atmosphere can compensate even more than you transport in the ocean. Okay, because we saw example. And in the generalized Bjerknes theory here, we not only want to know what kind of forcing you produce heat compensation, we also have another issue is that if I perturb at high latitude, how does ocean atmosphere heat transport in the remote places? Okay, so that's called remote problem. So let's start with the first one. In this case, we can simplify to start with slab ocean because we're going to prescribe ocean heat transport. Just watch how much is the atmospheric response. Okay, so we can use the energy balance model. That is very simple. You have the prescribed ocean heat transport in the ocean such that there's a convergence forcing the atmosphere. That's energy from the surface. Then, this is from the surface. Then on the top of the atmosphere, there's a long wave radiation, radiates out. That's a BT, radiates out. You get a warming, then it radiates out. Then the final thing is that the rest will be the atmosphere. They have to be transported and by the atmosphere. Okay, that's all the energy balance model. Okay. And in this energy balance, you write it down mathematically. It's basically order differential equation, second order differential equation. And the parameters you can, this B especially is the feedback parameter, you can ask the value about 2 or 3 roughly. And in this model, actually, when it's a constant coefficient, you can solve them analytically because you use the eigenfunction sine, cosine, or in the spheric case, use the Legendre polynomial. You can solve that. So you can explicitly calculate the Bjerknes compensation ratio. That is, if I have ocean heat transport perturbation, what is the response of atmospheric heat transport? Then you write it down. That is the formula. First thing, always smaller than 0. Okay, so in this model, if you perturb ocean, atmosphere always go the opposite direction. This just gives you an example. In this example, I prescribe the ocean heat this direction, this heat transport, and then solve the problem. You find that it just warm up here, very reasonable. You transport the heat warm, cold, and atmosphere transport opposite direction. Okay, and you look at the heat budget, and it's balanced out by the ocean heat transport is balanced, partly by the top atmosphere radiation, partly by the ocean atmosphere heat transport, and the ratio is about just we calculate in that formula. The mechanism actually is very simple. Okay, think about it. Suppose in the coupled system, I transport heat toward this region. Okay. Well, all the ocean heat has to come out. There's no damping in the ocean itself. It has to come out. Now you have 2 choices. Part of it is damped because you have this B larger than 0 means there's a negative damping to long wave damping to the top of the atmosphere. So you damped out. Well, you're damped out, then the rest will be transported in this direction. So you have to go opposite direction from where you prescribed ocean heat transport. So they have to be negative. And you can see the spin-up process. When you suddenly start heat transport in the ocean, the atmosphere goes the opposite direction. And so the temperature north, so the north part, warmer, south cooling, and the heat transport, the ocean atmosphere just opposite to this. Okay, and the Bjerknes compensation ratio with time is always negative in this case. So the mechanism is actually very robust. Now let's look at it more carefully, quantitatively. Look at this formula, okay? Now, if B equals 0, C equals -1. What is B equals 0? B equals 0 means my atmosphere does not radiate heat out. That's like rigid lit. That's obvious. Whatever heat come in the ocean, exact amount has to go out. That's why it's a perfect compensation. It's 1. Okay. Now, it is interesting. Well, in real world, we have damping, long wave damping, so it's not 0, so it's positive here. Now, in this case, the minimum compensation occurred in n equals 0. The n equal 1, sorry, n equal 1. That's a very large scale inter-hemisphere heat transport. So that's minimum damping. Minimum damping, it just depends on how big is it. It depends on the ratio of the feedback. The feedback is about 2 to 3, so you plug it in, it's about 70% compensation. Okay, atmosphere compensate about 70%. This just one example shows that the minimum compensation ratio as a function of this feedback parameter realistic regime is about 7%, 70%. Now it's also interesting to look at this. For small scale, n is very large, so this equals 0. This becomes a perfect compensation. It means if I prescribe ocean heat transport, has very complicated structure, okay? I have heat coming up in a structure. For this, the atmosphere completely compensated, one-to-one compensation, okay? Now mechanism is very simple. Think about this formula. This is a heat transport you prescribe as forcing. If the scale is very small, the derivative becomes very, very large. So the balance is between this heat transport conversion and the forcing. So the complete balance. So the forcing, ocean forcing is complete balance by the atmospheric heat transport. That's why complete compensation. Now, there are interesting examples, okay? And for example, in this case, Marshall had some experiments. They use a coupled model by the idealized geometry constant. My point is that you look at the global heat transport, total heat transport, very smooth. But look at the atmosphere and the ocean alone. Very wicky, okay? So they have very small scale structure. But the small scale structure, when you add them together, it's gone. Because they are completely compensated. Okay? So that's just consistent with the theory we talked about before. So in global, total coupled heat transport, it's very smooth structure. You don't have very little structure. Now this is another example we're doing. It's found some dust effect of Africa dust. So we're putting dust here, see what happens. But forget about the other point. I'm just looking at here. This heat transport anomaly produced by the dust change in Africa. The red is atmosphere heat transport anomaly, blue is ocean. You can see that they almost, at a small scale, they just almost completely compensate. As a result, the black is a total, has a very smooth structure. Okay, so high wave number, they tend to compensate. Therefore, in the total coupled global context, they tend to be very smooth, large scale. But we still have a problem. As I said, you have some parameter regime, you can produce even overcompensation. That is, you give ocean 1 watts per square meter, I can have 2 watts per square meter going the other direction. How can this be possible? Now, start with looking at this formula. This formula, if B is larger than 0, that means I always damped the atmosphere. This has to be smaller than smaller than 1, the value. Okay, so you have to have the so-called undercompensation. The only way you have overcompensation, this value is larger than 1. This has to be negative. B has to be negative. Okay. B is negative means my top atmosphere is positive feedback, not negative feedback. Now, you have a problem. Global climate cannot be positive feedback. Otherwise, we have runaway greenhouse, okay? So we are stable, we are not. But it is perfectly possible. Locally, you may have positive feedback, okay? While global, maintained. Well, this is the feedback analyzed from fully coupled GCM. Look at the black line. That's a total feedback at different latitude. In the tropics, they tend to have positive feedback. High latitude, negative feedback. As a result, the global climate is stable, okay? And this is CMIP. This is a IPCC model. You do the analysis, just look at this final net feedback, tropics, positive feedback, and extratropics, negative feedback, okay? My point is that you could have a positive feedback locally in a stable climate system. Now, the next minimum model to do this is you make the 2 box or two region. You can still derive the equation, okay? So now you see that if B1, B2 is local feedback in the 2 region, tropics and the high latitude, if they are in the same direction, B1, B2 in the same direction, okay, then it has to be, this has to be smaller than 1, so therefore the magnitude. So that is undercompensation we talk about. But if they are opposite sign, so if one of them is a positive feedback, okay, then I can indeed have this larger than 1 mean value. Okay, you can have overcompensation. And you can show that in this system. As long as the B1 plus B2 is smaller than 0, the system is basically stable. You can solve the eigenvalue stable. So it's like a global mean. As long as global mean feedback is positive, my system, global mean feedback is negative, is stable. But I can have locally, I can have positive feedback. Okay, so this shows one example. Okay, now in the model I have 2 regions. I still prescribe the ocean heat transport this way. I want to watch what's atmosphere heat transport. In my first case, it's like I did before. I have a constant feedback. They are negative here. So of course, this is a compensation ratio. So you produce your warm, high latitude, cold tropics. Therefore, the compensation ratio black is smaller than 1. So that's under compensation we just talked about before. Now watch here. I have global feedback remain the same, but I increase here, but I change this from negative to 0. Here, from negative 2 to even more negative. So global mean the same. But look at the response now. Now, because B equals 0 here, so here is perfect compensation because locally in the tropics here, there's no energy going out. So whatever come in has to go out. So perfect compensation. Okay, and you further helped in this region, even though it's more negative, you still helped to make them towards a higher which is ratio. Look at further. If I now increase this to a little bit positive in the tropics, but high latitude making more negative, so global mean the same. Now you can see here, you start to have overcompensation in this region of local positive feedback, and that will even spread into other regions, even though here actually is more negative feedback. Now one feature you see that if I have uniform feedback, it's a warm pool, cold response. It's like bipolar response, but the global mean remain more or less the same. But when you have the positive feedback locally, the global mean temperature is also changing. Not only the acidity gradient, global mean temperature is also changing. Okay? Why is that? Let's again think about this simple model. Let's do the experiment, thought experiment again. We transport heat this way, heat comes out. Okay, that's the same. Now, the difference is that this is a positive feedback. What does it mean, positive feedback? I have 1 watt per square meter heat come here. I have additional heat come in because it's positive feedback. Okay? Now, if that's the case, what else atmosphere heat transport go? The only way is to go back here. So you have this come in, this additional, so you have more heat transport back than what you prescribed at the beginning by the ocean heat transport. So that's why the local positive feedback matters. Okay? And the other thing you can see that because in this region, it's supposed to be warmed up, and then you have positive feedback, so you generate lots of heat. This transport back, so you produce a global warming. This here, originally you lost some heat. You want to be cooling, but because you suddenly generate extra heat from here, so you can still warm it up. So the entire globe will be warmed up if the downstream of ocean heat transport is increased, is positive feedback. Okay? You can have the opposite direction. If the upstream heat transport is positive feedback, then it's global cooling because you pull heat away, you lose heat, but you lose more heat. Then this is spread around. You got an extra compensation, but it's global cooling. Okay. So the point is that when you have local positive feedback, you can indeed generate overcompensation. And in the meantime, global temperature change, global mean temperature change. Okay. This might have some implication for some paleoclimate. For example, in Cretaceous, there is always one puzzle why the current model couldn't produce this reduced gradient. The global mean temperature is warm. One hypothesis is that the ocean heat transport increased. But if ocean heat transport increased, if the feedback, there's no positive feedback, you just simply reduce the gradient. You don't increase global temperature. Okay? So what you need, if ocean heat transport is increased, is responsible for this, the additional thing you need is to have additional positive feedback at high latitude. clouds, whatever. Some people talk about equal climate, have positive feedback. Then that will reduce gradient, increase global temperature. Okay. Yeah.
The polar amplification, is that what we have now? Is that
in polar amplification, yeah. In the current global warming case, I will talk about later. It's mostly actually you can have compensation, and the global mean temperature you have some change, not so dramatic in this case. Okay. This point, my point is, but this is different from the current global warming is that because you have radiative forcing. This is if the forcing is by ocean heat transport alone. Let's suppose radiation, no change, okay? Just to transport heat. If you have no positive feedback, the only thing you do is you warm it up, you coexist, no global temperature change. How do you warm up the entire globe? Then you need, in the region downstream, you also have positive feedback. Let's say cloud or some property change. Then it's like you mysteriously generate additional heat, right? Because that's a positive feedback. Then it's redistributed back, so it warm up the entire globe. So that's the point of this. Okay. Yeah. So for this part, the summary is that as long as the climate is stable, global mean is stable, then Bjerknes compensation is always valid if it's caused by the ocean heat transport. The second, if the net feedback, then it's so-called undercompensation. You transport 1 watt, 0.7 coming back. But if you have a local positive feedback, you could have overcompensation. 1 watt, I can have 1.2, okay, and global mean temperature change. And there are some other minor features I'm not going to deal with. So now let's go even further to the generalized theory, okay? Generalized Bjerknes compensation theory. See, here's a question. I can have general forcing. It doesn't have the ocean transport. Maybe greenhouse, maybe solar insolation, maybe some whatever, volcano, whatever. In this case, I perturb the climate. How is the atmosphere ocean heat transport respond? Okay? My first part is that you notice that I only perturb ocean, then see what the atmosphere responds. Okay? But now I'm doing more general case. This is some global warming response. Different models show the global warming. Some case you do see opposite. Most of case opposite response here. Although in the tropical region here, you see they tend to go the same direction. Okay, some here tend to go the same direction. So in this global warming case, it's not very obvious. Sometimes you have compensation, sometimes they may not. That's what the model says here. Now, we know, as I said, this is a natural example. When you have a short solar radiation come in, they tend to just go to the polar region. It's a collaboration response. How do we think about this? Now, this we have to increase the model complexity a little bit. Instead of using a slab ocean, I have to, in the ocean, also add heat transport, which I can parameterize similarly as a diffusion of the temperature across the ocean. So it becomes a two-layer model. And I was stuck on this for a while before I realized that actually it's a very simple problem. Because think about it. Let's think about this, Fs. This is surface heat flux. Surface heat flux change between. If I have surface heat flux change, look at the equation here. It's zero-sum game. I give to the atmosphere, I lose heat. So to the ocean and the atmosphere, the surface heat flux is opposite sign. So the response has to be opposite. So they should produce an opposite compensation response. That goes the same to ocean heat transport. In the steady state, when you have ocean heat transport, there's nowhere else to go. You have to produce changing surface heat flux. Therefore, you have to have a compensation response. That's the case we discussed earlier. When you have ocean heat transport response, it's always compensation. Okay? Now, that is, so it says that if I perturb surface heat flux, okay, then you should have compensation response because it's a zero-sum game. One gain, one lose, it's opposite response. However, from this point of view, you think about this. If I have solar radiation come in, well, that's a win-win situation. I got heat in both atmosphere and ocean. We don't have to fight. Let's just happily share them, go the same direction. So in that perspective, if I have solar radiation, I should produce a collaboration response. Same for the top of the atmosphere. If I have some perturbation falling in the top atmosphere, then that's the same for both atmosphere and ocean. There's no fighting between them, so it's a win-win situation. Both have to go the same direction. So before going to the mathematics, trying to solve this, we can think about this physically. If I perturb any parameter that results in surface heat flux change, I should produce compensation response. On the other hand, if I perturb top of atmosphere, it's external forcing, then I got a win-win situation. This should go to collaboration response. And that's exactly what happened in the mathematical solution. You can solve this, again, in the eigenfunction cosine become analytical solution. You can find that the compensation ratio, if I only perturb this ocean heat transport coefficient, that is, if I only perturb ocean heat transport, the compensation ratio, this form is very similar to what we just talked about before, okay? It's 1, then divided by this b here, okay? So it's a negative, so it's compensation response. Now, I didn't expect if I perturb other parameters here, so they all perturb surface heat flux, they produce quantitatively exactly the same compensation ratio. I was thinking they will be sort of more or less negative, okay, compensation, but I didn't realize they are actually exact the same compensation, okay? So it just shows that if you perturb surface heat flux, they are just the same, same response, okay, compensation. And if I perturb top of atmosphere, yes, they are indeed positive collaboration response. That was expected. Okay, so now actually this part of the problem becomes actually very simple, right? It just depends on you perturb, what's the perturbation forcing. If you perturb dominantly on surface heat flux, then atmosphere gain, ocean lose, or vice versa, then the response is opposite. That's compensation response. If you perturb the top atmosphere or short wave, then it's a win-win situation, then it's collaboration response. Okay. So the short wave response, that's obvious because you have the short wave response, short wave forcing, that's a collaboration response. Now, we have to be a little bit careful now on global warming case. The case of global warming is that it increases CO2. Therefore, the long wave radiation increase towards both the top and the bottom. Okay? Now, this one will give you collaboration response. This one will give you compensation response. So it's actually not obvious to a global warming response. You have to have compensation or collaboration, okay, from this perspective. So anyway, I did go to the theory saying that I'm not going to show that. In the global warming case, you have to go to secondary factors. The first order, they sort of canceled out. You have to go to secondary, okay? The spatial distribution of the coupled feedback become actually interesting factor. So you need atmosphere transport heat toward the north, but in the meantime, you also need a stronger damping in the tropics to make compensation response. Now, final question. As I showed you this GCM results, I perturb clouds in the Southern Ocean. My heat transport is always same direction and have very little response when you go here. And when they analyze the coupled system, yes, it is hardly circulation, subtropical cell change, and this seems like it's not give you a very strong heat transport response downstream. Same thing for this. When you perturb Arctic sea ice, and the ocean atmosphere heat transport can go the same direction, not opposite. That is what people think the ITCZ want to go. Well, let's think about this. This problem can be thought as actually coupled mode. It's like wave radiation. When I talk, you hear, right? That's because sound wave radiate to your ear. Here's the same, except now the wave is not the normal wave. It's not even Rossby wave. It's really some kind of energy coupled mode, okay? You have dxx here in the atmosphere, in the ocean here. So it's, you got an atmosphere, it's diffusive, but it's a stationary, For wave, you should have a partial T here, but we're talking about stationary wave, very long time. So in this kind of stationary wave, really the damping becomes scale, in the spatial scale, instead of in time damping, because you fix time becomes 0. So the only thing can change is space. The space becomes damped response, okay? Now, you can solve the eigenvalue in the damping scale here, eigenvalue. And there's one eigenvalue just for the atmosphere. That is, if I only have atmosphere, I should have this damping, because of radiation I have damping. There's another one for ocean damping, only for ocean damping. So now, let's think about the coupled system. The simplest case, if I have no coupling, in this system, if I have no coupling, you can solve this. You have two modes. One mode has exactly the atmosphere damping rate. In this case, atmosphere transport heat, no ocean response, okay? The other mode is pure ocean damping rate. Ocean transport heat, atmosphere has no response. It just, because there's no coupling, the two just go, independent. So this is kind of a simple case, but our real world, if you calculate regime, it's actually in the opposite case. It's a coupling much stronger than the top of atmosphere radiation. Because this radiation, especially the surface heat flux, that one you actually include a turbulent heat flux. That's very strong, okay? It's almost 5 times larger than the top atmosphere pure long wave radiation. So the realistic regime is this much larger than this. So this is very big. Coupling is very strong. In this case, the coupled mode, you can solve this, interestingly. One mode, the damping rate is atmosphere damping plus ocean damping. So this is a heavily damped mode, okay? It's two together. Also interesting, you look at the eigenfunction structure. Atmosphere, ocean, they're always opposite. So this mode is a compensation response, but heavily damped. The other mode is very, very weakly damped, just the top atmosphere radiation, very weakly damped. Now, in this case, the eigenfunction structure, they are in the collaboration response, okay? So what this tells us is that in the coupled system, we have two coupled energy propagation modes. This is not Raspberry wave, not like that. It's just energy coupled modes. One mode, compensation mode. For example, I can excited by surface heat flux. Then we can have compensation. We talk about how it's propagating. Very slowly, opposite direction, quickly damped. The other mode, let's say this one. Suppose I use top of atmosphere. I produce collaboration response. They propagate quickly and very little damp. They can propagate far away. Okay. And so because the collaboration mode has very little damping, so if I have a forcing here, the far region response should be dominant by the collaboration mode, not by compensation mode. Compensation mode is damped from the region of forcing. Okay, it's sort of like in the climate dynamics, in the atmosphere-ocean dynamics. There's one thing called the Bjerknes mode, where the upper layer, lower layer go opposite direction, whereas the barotropic mode they go the same direction. But here is a completely different physics. Here's completely different physics. Now you might say, well, this is mathematics. This mode is heavily damped. This mode is not heavily damped. I would say, no, it's not, because the physical mechanism is very simple. Why the compensation mode damp fast? It's because, as I said, compensation is mostly exciting surface energy flux. Surface damping is very strong. You have the latent heat, sensible heat, very strong damping. You quickly damp it out. Well, this mode, because they don't involve too much surface energy change. It really just top of atmosphere energy change. Now that's very weak damping, because that's just long wave radiation, Steven-Boltzmann formula, just very weak damping, okay? At least, it's probably 10 to 20% of this, okay? So that's why physically, this mode should be, less damped, while this mode is heavily damped. So, for the remote response, we have two kinds of mode. And remote response tend to be dominant by collaboration response, except this one thing. These are all coupled through surface ocean-atmosphere coupling. I could have, if I perturb Atlantic meridional overturning circulation, they sneak out from deep ocean across the entire hemisphere, deep western boundary current all across. So they transport heat. Then they come up surface heat flux affect atmosphere. Now, in this case, the remote teleconnection could be very efficient. Now, you can indeed produce compensation, just like the first part I said. If you give ocean heat transport, then atmosphere can have compensation response. Okay, so the conclusion is that in the coupled system, when you perturb it, if you don't perturb AMOC strongly, then you have to have collaboration response because the coupled mode is less damped. But if you perturb AMOC very strongly, then you can have a compensation response. Okay, so it depends on how you perturb it. And how much time I have? Yeah, and this just some. I'll just show you one example. Okay, so this in the model, what I do is that I only perturb. I can't remember. Yeah, I perturb the surface flux. Perturb this parameter. I suddenly decrease this parameter. Okay, decrease this parameter. So we know that this perturbed surface heat flux, then it should produce compensation response. Yes, as you can see here, my response in this region, that's why forcing region in the south hemisphere region, because I reduce this. So atmosphere, because ocean gain less heat, atmosphere lost less heat, so atmosphere warm, ocean cools. And ocean atmosphere heat transport opposite, that's compensation response. This is ratio ocean divided by atmosphere heat transport is negative. But then this part, there's no perturbation. Everything comes from here. Like I'm speaking here, whatever wave come out, high pitch or low pitch, coming from here. Here, there's no forcing. Okay? So you can, it's field propagation. So you can see this compensation response quickly damped. And actually here, it becomes actually positive. So the ratio actually becomes positive. It becomes a collaboration response in the remote region far from here. Now it's opposite if I perturb it with top of atmosphere heat flux. In this case, I reduce a damping on the atmosphere on the top. So both atmosphere and ocean warmed up. Just I lost less heat on the top, everybody's happy, we just warm up. Once you warm up, both atmosphere and ocean produce heat transport towards the north. Now you look at this one heat, this response propagates far away, very robust, all the way towards this region, and the Bjerknes compensation is always positive. Okay, so it just shows that if you don't excite thermohaline response, then the remote response is dominant by the collaboration response. I think this explains, at least, is a major reason, this couple GCM results. In this case, you perturb south hemisphere, and then atmosphere ocean goes the opposite direction. It's collaboration response remotely. Same thing for this, you perturb Arctic region, ocean atmosphere goes the same direction, the collaboration response. And we actually did another experiment in the 40 couple GCM. It was for some other purpose, not for this purpose. But it happened that we produce same direction of heat flux in the south hemisphere. Then this direction, you can see they all go the same direction. So this is collaboration mode. In another case, we produce opposite response of heat flux, atmosphere, ocean in the southern high latitude. But then look at this region. Then they also go to the same direction. Initially, they're opposite direction, but later they damped out. The Bjerknes the compensation mode damped out. You're left with them going the same direction. Okay, so I think it's an indirect proof in the GCMs we have. Now, in the Slab Ocean model, it's very easy to change the ITCZ. That was because in Slab Ocean model, you prescribe the heat transport. So you sort of implicitly assume I already have this remote propagation all the way through. Then you come from the surface, you perturb the atmosphere budget, then you change the ITCZ. Okay, so that's in the Slab Ocean model. So in the fully coupled model, this actually perturb high climate, it should become a fully coupled mode. Then the propagation becomes much more less efficient. And I think this is a later paper after I wrote it. I submitted my journal. John Marshall, they did experiment. They were doing fully coupled model, then they perturb high latitude. They want to watch how much ITCZ changes. In Slab Ocean model, the ITCZ moves 2.5 degrees. Exact the same change in coupled model, 0.5 degree. Okay, and they did specify there was a coupled ocean atmosphere coupling. Okay, they were diagnosing their coupled model. They found that there's ocean atmosphere coupling there, somehow trying to cancel this. So I think this can be explained with my simple theory in the first order. So here's a summary. For generalized problem, Bjerknes compensation, which is really just you perturb a climate system, how does the atmosphere ocean heat transport respond? That's a general problem. Okay. And so number one, if it's perturbed by ocean alone, then as long as it's a stable climate, it's always compensation. And in that case, if you have a local positive feedback, you can even produce positive feedback in global mean temperature change. But more generally, it's that if you perturb a surface flux, dominant surface flux, then you produce compensation response. Otherwise, if you perturb top atmosphere response, then it tends to be the collaboration response. And finally, for the remote response, the compensation mode is heavily damped by the interface air-sea exchange. It damped quickly. So it's very hard for them to go away. But the compensation response is only damped by the top atmosphere radiation, so they can propagate far away. So you start your perturbation with a mixture of compensation mode and the collaboration mode. But the compensation mode quickly damped, the collaboration mode propagates away far distance. So in the remote region, what you observed actually is a collaboration response. That's my explanation of the GCM experiments. Okay, that's all. Thank you very much. Yeah.
Questions?
Yeah.
So I'm surprised how much I enjoyed this talk when one of the punchlines is that some of my earlier stuff was quantitatively wrong.
Well, not wrong. It's just stimulated. Yeah.
I just want to see if I'm interpreting and understanding correctly.
Yeah.
So in the experiments that Gen K did,
right.
You showed the sea ice, both hemispheres, southern ocean clouds, sea ice.
Yeah.
That's a coupled model. There's not much of an ITCZ response because the AMOC is not involved.
Yeah, it's not too much perturbed.
But in Zheng and Delworth,
yes.
doing water hose.
Yes, exactly.
They big ITCZ
exactly.
response because it does involve the
Yes. Yeah.
So in thinking about paleoclimate, we could still think about big ITCZ shifts happening. Yeah. But they're more likely to happen only if the AMOC is perturbed.
That's my conclusion.
Okay.
Yeah.
That's cool.
Yeah, it was, well, before I started this, it was just puzzling. On the one hand, I feel this is a fundamental problem, but I don't have a rule of thumb. You know, you see sometime happen, lots of time happen.
And by the way, just another thought.
Yeah.
So in the slab kind of experiments, there's almost always going to be overcompensation.
No, if you have local positive feedback.
But there almost always is going to be local positive feedback, water vapor feedback, and albedo feedback.
Then the net has to be. Well, in that region, you have to compensate the negative to become. Yeah. If you have that, you could. Yeah.
These are all the time invariant solutions, but as we know, the climate is not time invariant.
Yeah.
So do you see different perturbation timescales?
Yeah, I didn't talk about that. You basically, we have a paper on the time variability part. Actually, let me just check on this. Well, the conclusion is that when the time scale is like about decade or even longer time scale, then the solution is the compensation is more or less right. If it's interannual, it doesn't work. Like El Nino, too fast, it doesn't work. But it's long enough when the transport the heat storage is no longer, in the ocean, no longer dominant factor, you will have them compensate. So this shows up in GCM experiments. I sort of didn't show that figure here. Okay, in GCM, you can see that these are different experiments. This is atmosphere-ocean correlation, heat transport correlation at different latitude. Okay, in this case, you have them. This is climate variability. In a just fully coupled ocean, you measure the ocean atmosphere, then you do a correlation, right? This is negative. But I want to show is this two. This is time scale. This time scale. So atmosphere-ocean correlation at mid-latitude somewhere, you can see that if the time scale is very, very short, there's no compensation. It's when the time scale becomes long, they become approaching the steady equilibrium response. So eventually, you have the compensation response we talk about. So the solution will be, it's equilibrium theory. So you have to have the system fully adjusted, not fully adjusted, dominantly you adjusted that, then you could work. And qualitative, it's also always true. Lower frequency, the more likely the equilibrium solution is correct. But if you have very high frequency, this doesn't even apply. Yeah. And also for the paleo, just the thing. I always didn't quite understand before, in the Cretaceous, global warming, the ocean heat transport increase is one hypothesis, right? People say. But I always thought, well, you transport heat, you warm it here, but you cool it here. How can you get a global warming? Now here it's clear, okay? If you transport heat to high latitude, in the meantime, you have a positive feedback. Like Eddie Zipman, some people that are doing simple model, they want to have extratropical positive feedback because clouds change or whatever. Then yes, you think about now the high latitude region is a region you generate extra heat because it's positive feedback. So you give a little bit of heat, then you produce more heat, you come back, warm everywhere. Then it goes together, okay? It could be the opposite because Ray Peter Hamburg used the same thing, but focusing on the tropics, it could become called thermostat. Tropics, positive feedback, but you transport heat away, and you lose heat. You lose heat, so you radiate heat from subtropics, where you have a stronger damping. So instead of damping the tropics, you're damping the subtropics, where there's a stronger damping. So then the global average, that's why you can stabilize this. Stabilize. Even though tropics, you can have positive feedback. So you still don't have runaway greenhouse gas because global mean is still stable and it can still damp here. In this case, because you transport heat this way, then you lose some heat in the tropics, but it's a positive feedback. So you lose a little bit heat, you lose more heat. Okay, so then you can stabilize the global mean. Not just tropics, stabilize the global mean. So it really depends on heat transport and the local feedback, the relative position, I think. I don't think people have thought about this so carefully. And this just make it more, this point, relation to global mean, just make it more explicit on this part. Yeah.
More questions?
Yeah.
A couple of climate models, the Bjerknes compensation ratio depends on which latitude you are.
That's true.
So
Yeah.
generally, if you are looking at the high latitude, the Bjerknes compensation ratio is higher. So I'm wondering if your theory can explain this.
I'm not sure if that conclusion is right. Let's see, look at this. Okay, so this time scale. Yeah, I don't know if that conclusion is right. High latitude is higher. I don't know if it's right. It's not very obvious to me because I didn't divide this here. Just look at this example. If you divide it, ocean atmosphere. I mean, these are just experiment posting. So it's hard to see if you divide it, it's getting higher or lower, because they're both getting, I don't know if that's true. Yeah, yeah.
One more round of applause. Thank you.
Yeah, all right, thank you very much.